Your tap on the 15th floor doesn't have a plumbing problem. It's obeying physics nobody explained to you. Municipal supply is engineered around an average static head and a peak demand curve sized for low-rise buildings for flat streets. Above the 12th floor, without booster intervention, the available pressure at your riser inlet already drops below usable hydraulic head. This isn't your building's bad luck. Forget what feels right to your instinct as a city dweller. Friction head loss inside the pipe, plus the elevation head you have to overcome with height, plus the pump's physical limit. These three things together prove, mathematically, that your high floor is, by design, last in line. Aging mains, demand spiking at the same hour every single day, and a regulatory pressure floor nobody told you existed. That pushes the whole system to its limit exactly where you live. If you already know this is bullshit, drop a comment with a rational or a fragile, because the next piece is even more uncomfortable. Utilities run a formal staged restriction policy with a minimum residual pressure threshold, protecting the main network and guaranteeing fire flow before your tap ever sees a drop. District metering areas and pressure management algorithms trigger scheduled rotations without notifying upper floors. This isn't malfunction, it's protocol. Stay rational, because that distinction separates people who react too late from people already 2 steps ahead. The system tries to fix this with the pressure-reducing valve and its inverse, the pressure-sustaining and boost control assembly. It protects risers and fixtures from overpressure with a set point, a flow coefficient, and a hysteresis band most building managers don't even know exists. The mechanism is simple. It throttles flow to keep the pressure differential across floors inside allowable range. It was born as a plumbing code fix for overpressure, not for scarcity. And that's exactly where it turns hostile. Misspecified, it becomes a choke point precisely when supply is already weak. That's not sabotage from your building's administration. That's a valve doing exactly what a different problem trained it to do. You need to recognize booster pump sets and variable frequency drives the moment you see one in the basement, because that's the hardware giving back the hydraulic head elevation stole from you. Staged pumps, redundancy. So one unit failing doesn't kill supply. Frequency control holding constant pressure, suction limits so it doesn't cavitate, check valves so water doesn't backflow. This comes straight from industrial pump room practice adapted for residential towers. Hardened and ready, because the distinction here is brutal. This hardware converts electrical energy into hydraulic head. No power, no controls, no water on your floor. Period. Your comfort on the 15th floor depends 100% on the grid staying up. I ran a spreadsheet simulating a 12-hour blackout in my own building, and the number was worse than expected. The rooftop header tank creates pressure independent of main supply at the moment of use. It stores potential energy, height times gravity times density, feeding upper zones even while the main network is on its knees. This comes straight from classical waterworks and cistern engineering, from before reliable electric pumping existed. The distinction that matters: passive, simple, resilient compared to active pumps, but constrained by rooftop structural load and contamination risk if not sealed right. Prepare in silence, because whoever already calculated their own tank's usable volume knows exactly how many hours of real autonomy they're sitting on. Modern buildings solved this by splitting the structure into hydraulic zones: low, intermediate, high, each one with its own riser, its own pressure-reducing valve, its own dedicated sensor. That creates a static head offset between zones, with isolation valves and cross-connection controls so one section doesn't interfere with the next. This is standard multi-story plumbing code practice, and the real distinction is this: instead of one giant pump trying to overcome the whole building at once, you get smaller systems focusing exactly where demand actually bites. If you've ever been pissed about pressure swinging floor to floor inside the same building, that's it. The zoning is probably missized. Prepare in silence while the rest of the building doesn't even know this problem has a name. You need to understand the Hydropneumatic tank before we go further, because it's the piece smoothing out the short-term fluctuation your pump alone can't handle. It's a closed vessel, air charged over a bladder, storing pressurized water for quick demand spikes. Pre-charge pressure, drawdown percentage, pump cycling rate, this is engineered, not guessed. The mechanism is purely physical. Compressed air stores energy, so the pump cycles less and still meets the instant peak. This is standard industrial pump room practice adapted for residential use, and the distinction matters more than it looks. It fixes short-term fluctuation, it does not replace long-duration storage. Whoever confuses the two is exactly who runs dry in the middle of a prolonged shortage. Before I show you the actual twist in this reasoning, quick note. If you want the actionable intel before the grid goes down for real, subscribe and stay on this, because the next block completely flips how you read building automation. I used to think, like most people, that digital controls and smart meters solve rationing more fairly. They don't. I found this out simulating a power failure with telemetry offline. And what actually sustains pressure on the high floors when the digital system drops is something far older. A manually operated gravity-fed standpipe and rooftop cistern, both independent of pumps, telemetry, and grid power. Simple valves, manual isolation procedure, gravity head calculation, that's the whole system. It comes straight from pre-electrical urban water infrastructure. Prepare in silence, because this is the twist nobody in your building wants to hear. Cutting-edge automation fails exactly at the moment you need it most, and the analog solution, ugly, manual, app-free, keeps delivering water when everything else locks up. You need to inspect automatic balancing valves, solenoid isolation valves, and flow-limiting orifices buildings deploy to throttle usage riser by riser. Flow coefficient, response time, power draw, fail-safe position, that's what dictates how the valve behaves under stress. The mechanism is proportional or on-off control tied to a flow sensor or a scheduler. This comes from industrial control adapted for plumbing, and here's the catch. A poorly tuned valve creates de facto rationing just by pressure drop, not by any fair allocation criteria. Nobody decided your floor drinks less. A badly tuned valve decided that by default, silently. I spent an afternoon reading smart meter specifications, and the result was uncomfortable in a way I didn't expect. Advanced metering infrastructure uses pulse, ultrasonic, and magnetic meters to measure consumption per riser or per unit, feeding control loops or billing algorithms. Accuracy, minimum detectable flow, tamper vulnerability, integration through industrial network protocols, all part of the package. The mechanism is closed-loop demand management that can throttle your consumption automatically once a threshold hits. This comes from utility billing tech, and the distinction nobody says out loud. This system enables real automated rationing, but it depends entirely on cybersecurity and grid power to keep functioning. Prepare in silence, because a cyber attack at this exact point in the chain is more realistic than it sounds. I need to flag something most people ignore until it happens. Fire protection risers and wet or dry standpipes have code-mandated priority for pressure and flow, and they siphon off available hydraulic capacity during any rationing event. Dedicated mains, minimum design flow, constant pressure maintenance. That's the mechanism. Valves and Siamese connections that bypass the resident's tap entirely in an emergency. This comes straight from life safety code, and the distinction that carries weight. Legal priority can make your residential supply secondary at the worst possible moment. Your building isn't hiding this out of malice. It's following the law. And the law doesn't prioritize your shower. Acoustic sensors, pressure decay tests, and flow imbalance analytics get used to catch hidden leaks, silently draining a building's entire buffer. Sensor sensitivity, placement strategy, false positive rate, that's what decides if the system actually works or just cries wolf. The mechanism is differential flow analysis against a baseline with automatic isolation triggers to preserve stored water. This comes from industrial leak detection adapted for buildings, and the practical distinction, proactive leak control cuts the need for behavioral rationing and stretches the reserve you already have. Hardened and ready, because an undetected leak is rationing you're inflicting on yourself without knowing it. You need to understand generator sizing, automatic transfer switches, and fuel logistics to keep the pump running through an extended blackout. Rated kilowatt output against the pump's starting kilovolt amps, runtime, maintenance cadence, that's what decides whether your generator survives the load or trips on the first surge. The mechanism is simple. On-site generation restores power to booster and control systems during a grid failure. This comes from building resiliency practice and the real distinction. A fuel-limited generator turns a long-term shortage back into a storage and consumption planning problem, not a pure hydraulic failure. You solve the electrical problem only to discover the new bottleneck is how much diesel fits in your basement. I spent a week drafting protocols for neighbors, and what came out of it was simpler than it looked. Per apartment isolation valves, scheduled draw windows, fixed per unit allotments, and a manual transfer procedure between points. Enforceability, ease of use, sanitation safeguards, that's what decides if a protocol actually holds or turns into chaos. The mechanism here is governance plus simple hardware, letting people limit non-essential consumption without compromising basic hygiene. This comes straight from wartime civil defense and historical rationing practice, and the distinction that closes this reasoning. A well-designed social protocol is usually cheaper and faster to deploy than any new piece of hardware. Prepare in silence, because the agreement you make with your neighbor might be worth more than any new pump. The long-term fix is distributed cisterns, elevation-aware municipal loop upgrades, dedicated high-zone mains, and decentralized microgrids keeping pumps running through grid failure. Capital cost, hydraulic redundancy, full life cycle maintenance, that's what separates a patch job from a real structural solution. The mechanism is engineering the supply curve itself, pressure against elevation, instead of forcing consumption limits on whoever already lives on the highest floor. This comes from historical waterworks modernization, and the final distinction settles everything. Fixing the hydraulic inequality at its root is what stops the high floor from functioning as a de facto rationing zone. You don't have to accept that as your address's fate. You have to engineer your own immunity to this kind of failure, understand the system deep enough that you never depend on luck to turn on a tap again. This wasn't a plumbing lesson. It was a map, hardened and ready. Stay rational, keep it quiet, get harder to disrupt.